Thanks for catching that. Okay, hopefully you hear me now. Oh dear. Appreciate you saying something though. I'm only a little slow to notice. All right, so test passed. Let's commit. Whoops. Commit. Oh, am I on the wrong? There we go. Rename Elm types to Elm type. Okay, now the real thing, I think we want to say that every tree has some sort of type, and let's find out what that type is. Okay, cool. um, so the type. All right, so basically, I think we just have to blast through the case statement and match all these things. So let's get a tree tests, which we don't have yet. And I don't bother making it a test file because it's just got so much junk I don't want. I know you can set your own templates, and I just have to do that one of these days. All right, so we will steal a little bit of stuff from up here. I guess that much. And this is tree tests and close. Okay. All right, so we just want to verify the types of various trees, and I think we'll test type of tree, and this will test a bunch of things, but let's make some trees. Okay, so ignored, I guess these things. Where's Elm type? Error. We may have to have a, I don't know if there's a void kind of type, but let's check something. So I'm going to say check type of, and I'm going to make a new tree. Let's see, tree.integer value type. Okay. Tree tests. A value 3, and the type is Elm type dot number. It's weird that it's not int, but that's the way it goes. Okay. And I just am assuming I'm going to need this little helper function because I want to do these things. So it takes a tree of type tree and a expected of Elm type. And I don't know if we're being redundant, but this should, well, if we actually did something with it, assert equal tree.type is expected. Okay, I expect this will fail. Error is not equal to number. Okay, so our trees need to pull out the type from an integer value. Okay, so let's put them in more or less the order they're already there. Integer. We don't care about the name, the value, but we do care about the type. Now, I don't know if we can, let's see it pass. Can we fold these together? Yes, we're writing in Swift. We're writing a Swift program that's supposed to read and interpret Elm programs. So we're working on the if statements in Elm. And we've got the parsing of it, but we haven't quite got the semantics of it. Okay, and how do I ignore this? Only in a pattern on the left side. Can I do that? I think. No. Well, let's let value. Does it have a suggestion? Yes, it does. Case integer cannot be used. Am I doing that? Is that okay? Good. Okay, remove let. Back where I started, leaving out that dot is not recommended. Okay. And should pass. Now I'm curious if I can take this out. It's kind of, let's see, comma, custom value. All right, does that compile? It's interesting if it does. Wow, okay. Because they're two totally separate types. I guess they're compatible, which is good. All right. Let's get our tree test. Let's check a float. Type is elm type dot float. And we're looking for elm type dot float. It's a little simplistic at the leaf level, isn't it? All right, this should fail. Okay, and we have integer. Let's add float. We'll go ahead and add a test for custom type. Now my tests are a little unusual. Usually I'm invented the name arrange active search, and I'm usually pretty strict about doing it. But in a case like this, it's just like run through the exact same test with a bunch of different arguments. This is more like a parameterized test to me, although I'm not writing it in a parameterized style. But we have a helper function and then a bunch of things that just run through. Otherwise, there's a lot of boilerplate and it's all kind of boring. I think these are pretty clear what's going on. Custom value and the name, let's say bool, and the values true. Well, I'll make it my bool just to be my type. T1, T2, okay. And, well, am I messing up my tree already? A custom value. So it wouldn't be the type name. It would be the name of the value. So let's take value 1. This is elm type dot custom type. The type name is my type, and the values are v1, v2. Okay. And the expected type is really this. A little verbose, but I don't know if I can line these up in a way that, okay, let's see where our parens are going. M type, custom type, my type, v1, that should end that. That should end the custom value. Then a custom type. Now this I think will pass. Okay. I don't know if it's just to make it fail. Okay. All right, so we got those 3 trees done. Now we want to do if expr. Oh boy, that's going to be a challenge. Because the type, I don't know, I'd like to say, okay. Uh, it's sort of Java-like, Swift. The thing that's different is these enums you can, well, Java sort of does this now too. You can attach extra values to them. So that's all that's going on here. We're trying to build up these parse trees, so they have leaf nodes that are like integers, floats, and so on, and then interior nodes that are built up out of them. So this if expression is our first interior node, and it's definitely pushing some stuff. So okay, so these 3 are literal types, and so they just have their own type. The if expression, the type of it really should be, it's kind of the union of the left and the right. I don't know how we're gonna make that go. I guess we're gonna defer it to somebody else, basically. So we have, we don't care about the condition because that's always boolean, so that's ignored. We want to say let left and let right. Okay, so 2 miss 12. What language are you usually using? Okay, we need a statement. All right. Well, let's I need to defer this. I guess I'm gonna return left. Oh, I don't even have my test for this yet. Let's not go backwards too much. We'll take a boolean. His type is elm-type.custom-type bool. Okay. Yeah, Python's cool. My buddy Tim Ottinger loves Python, and whenever I have to dabble in it, he's always got a amazing little tricks of working with it. Yeah, but for me, it's more of a language I just get in there once in a while and do something, but not enough to really develop. I've done a fair bit of Java though. Yeah, well, this is kind of starting in the middle, I guess I would say here. But yeah, it's the stuff we're doing so far. I don't know. Bounce over the parser a little bit. It really is. I mean, it's Java like. I mean, C like, any of those things that C sharp, whatever. Um, the thing going on here that's kind of, we got these little recursive functions, expression, and we can let the expression do the whole thing. The try catch is a little different. You say do catch and you say try in front of the only the statements that could throw exceptions. So it's a little pickier that way. It requires you to say throws on the method if it can throw. So it's kind of picked that up from Java, which of all the things I'd like to get rid of in Java, I don't know, that's the one that gets my way a lot. I'd rather you could just throw. I would almost rather you could just say I can throw and throw in any case, rather than if you change your mind, you end up propagating down. But yeah, it's mostly Java like. These enums are a bit different though. I'll certainly do that. Okay, let's see. So we got this custom value. This maybe I should pull this out. Let's let boolean equal this stuff. Bool type. Is that. So we're saying Boolean type can take either string true or false. And if you see either string, you know your type. All right, and so with this, I'm gonna make this one use that as well. And just make this a little easier. Okay, so let's change that one. Now we're going to take a tree with custom value bool type. That closes the tree. And we need a left, which is an integer. 3 elm type dot number. And another integer, because our trees take the 3. Whoops. Number. Okay, and I'll work on the format here just so this thing's readable. Well, this whole thing is a tree.if statement. If expression. Try and get the 3 pieces visible so we can kind of make sense of it. So an if expression has 3 parts, and then we have a type we're trying to match, and this should be elm type dot number, I think. Okay, and a print here. Am I balanced? Okay, this should fail. Okay. Yeah, data science. It really seems like Python's really done well in that area, taken over kind of. Um, it's a nice language. It's not a heavyweight thing, and it's got some nice functional stuff and some nice processing stuff. Yeah, that's cool. Let's see. So error not equal to number. So which one's failing? Well, our type here failed. Okay, so let's get back to tree. Case if expression. Okay, so how are we going to take care of one of these? Well, I'm going to delegate dot. So we have a type elm type. Left is an elm type, and right is an elm type. And I really want to ask the type to just make the decision. So I think it's joint, or it's like it's not the super class, but it's sort of the, I don't know, shared type, something like that with right. Okay, I'm pushing the job off to somebody else. Okay, value of type tree. Oh, right. So I have to get left dot type. So this is recursive shared with right dot type. Okay, it has no member shared type. So let's go here. We're just kind of working our way in. Okay, so I can just say extension elm type and put my own function out there for it. It's probably a little more idiomatic. I'm not really a Swift programmer. I've just been dabbling in it heavily for a year and mostly on my own. So I may do weird stuff sometimes. But anyway, we're making a shared type function, and it's going to take a self and other of type Elm type, and it's going to produce an Elm type. Okay, and I think for now. All right. Thanks for following. Nice to see you. Hope to see you again sometime. Good luck with the Elm, the data science stuff. That's cool beans stuff. All right. So we got a shared type. I'm just going to return self for now and get through my tests. All right. Let's stack that up though. My to do. I think we're gonna have to do something with this. Well, we're doing the condition must be bool. That much is there, but we need to make sure make Elm type dot shared type do the right thing, whatever that is. We'll have to figure it out. Okay, and where are we here? If tests. Okay, I think we've done our bulk of our tree, and I'm going to make this an extension too, just to kind of be a consistent style there. Enum extension tree with that. Okay. So we don't have. We've got 1, 2, 3, 4. 1, 2, 3, 4. Ignored. Well, I guess the error node should be an error type. Ignored. I don't know what to think there. We'll have to see what. Let's make both those be errors. I think that's a legit thing. So check type tree dot ignored. We expect Elm type dot error, and same thing for error. Whoops. And those should pass because we're defaulting it as type error. Okay. Very good. Let's commit this. So we make trees know their type and enforce boolean on if conditions. All right. Okay, so good. All right, so let me update my to-do. So this is the 4th, 2021-0204. And the story is handle if statement. I mean, last time we did the parsing, kind of a task. This time we're saying condition must be a bool. And I think we're enforcing that at this point, right? Elm type.shared type. Then an else clauses must be compatible. That kind of gets to the shared type. So I guess what I want to enforce. Should my statement just have the type in it? Maybe it should. All right. Let's see. Well, we're at the point of being a good time for a break. So let's take that break. We'll just take like 2 minutes. we'll take the break, come back, and handle the then and else clauses compatible thing. I think this shared type, maybe it's joint type, but I think that's getting at the right thing, and maybe our if node should contain that too. So we'll come back and tackle that. See you in a bit. Hi, welcome back. All right. So I guess we've done something. We've done enough to see that there should be a shared type on our if statements, and we've pushed that into the tree. I'm thinking maybe this condition should have its type. Maybe everybody should just be trailing a type along with them. It would simplify this. We have to compute this stuff anyway, so let's do that. Um, let's enforce the joint type on our if statement. So that's really we're in our parser and parse if. Okay. How can we check that? Well, the parse gives us a tree, right? Parser parse gives us a tree. Okay, so we could look at the type of the tree, I guess. That's legit. Okay. Function test. Well, if with two integers has type I don't know, number, I think. Let's find our Elm-REPL. Okay. Three is a number. Okay, so, there are ways to get integers. I know, like, I think it's 3. I forget. I don't even know what this operator does. 3, 2. Yeah, so I don't know if it's is that a modulo thing? 5, 2. No, it's a integer. It's a divide and truncate thing, I think. Let's see, how do we know it's a truncate? Well, if we do 11/3, all right. Well, let's do 16/3. Should be 5 1/3. It rounds off 17/3 and 18/3. Okay. But anyway, you can have operators that get you to int. All right. Let's try that. If true, then 18/17/3, else 21 400. Oh, if true, then this, else that. It's an int. Let's try false. Int. Interesting. Wow. So the joint type of a number and an integer is int. Let's try, if true, then 17/3, else 4.5. Yeah, okay. The then branch has type int, but if we just did 17, what goes? 17 of float. So int and a number. I don't know. This is a little weird. We're going to have to figure these out. Okay. But we need to do a parse. So let's do this. And let tree equal parser.parse. Okay, and we want to assert that if true, then 3, else 2. We want to assert equal tree.type should be number. Elm type.number. Okay, and we're gonna encode this REPL. Make sure it's what I saw. If 3 then 2, 3 is a number by itself, 2 is a number by itself. Both types are number. Okay. So we don't. Well, let's run the test. We predict failure. No, I don't. I guess 3 is already, it's just bubbling up to the left. Okay. I don't have a way right now to create an int. Let's take this case, 3.5 else 2. We expect float. And if false, we still expect float. All right. Type.float. This will certainly fail. No, it won't. Let's get a test that can fail. Let's do 3, else 2.5. All right. Elm REPL should say float. Okay. And this test should fail. Cool. Okay. So I'm going to use this test as an excuse to test my shared type on Elm type. Okay, so, and I'm going to rename this to joint type. Is not common type? I don't know. Joint. I'll try joint type. Okay. Let's see. So, okay. So let's push this test that I already. Okay. So, and let's do Elm type tests. And again, I guess we haven't done any of those. They were just enums. Swift file. Elm type tests. And we'll borrow the front. Oh, let's push this. We handled type of tree nodes. Okay. All right, so the Elm tests, let's take the front, this stuff. Cool. Okay, so we want to test this joint function. Elm types, let's get it over here. All right, so error joined with anything should be error. Let's check that first. So we'll do function error joined with anything should be error. All right, so let's create an Elm type. Let's take, well, we can do it in one line, I guess. We expect, can I say dot error? To be joint type of number. I may have to put the qualifiers on. Should be error. Is it going to know there? Okay, yeah, can't infer Elm type. Okay. Should fail. All right. If nice, and I'm going to flip it. Elm type dot number joint type with error. Well, let's do float. All right. Excuse me. All right. Error types are good. What else do we got? We got number, float, and custom type. Okay, so the floats. Well, let's see what happens. All right, so number joined with number is number. Okay. I don't know. Maybe I pull out a check function, a checker helper. Joint type. Okay, left of Elm type, right of Elm type, and expected of Elm type. All right, so we want to say this. Elm type.error will be left, joined with right should be expected. Elm type.error joined with elm type.number. And you know, I sometimes have seen this done, and that might be a good clarification. Okay, cannot convert value of Elm type. Oh, let's call our function. All right, now check joint type. Well, if both types are the same, the result is the same. Let's check that instead. Same type or type joined with itself. type joined with same type yields same yields that type. Okay, so let's check elm type dot number joined to elm type dot number should be elm type dot number. Okay, and this should fail. Well, no, it'll pass now, but we can safely pull out if self equals other return self. Should still pass. Okay, so now we know we have two different types, neither of which is error. Okay, and let's if we're going to have to negotiate through these cases. So if you combine number with float, you get float. Is that right? Let's try it again. If true, yeah, that's what we just did there. If true, then 3 is a number and it's a float. Okay, so float with number float joined with number yields float. Elm type dot float right is elm type dot number, and the expected is elm type dot float. Okay, I think this will pass the way we are because we take this left, but we'll reverse it. Is it always symmetric? I think it is. All right. So let's take right joined with left. And some of these will fail. This last one, I think, only. Right. Okay. And so I think this, we did error number, float number. That was checking two different things. That's reasonable enough. Same type, can't show it. Joint type, float with number yields float. Okay. And it failed only the second one because of our switch. Okay. So if I don't know, these cases, we have if self equals dot float and other equals dot number, we're going to return number. And conversely, if self equals number and other equals float, we're going to return number. Whoops. Two failures. Number, did I say the right thing? No. All right. Float and number combined is float. Yes. Okay. And I think we've, oh yeah, custom types now. Must be equivalent And, or let's see, equivalent custom types. No. Different custom types yields error. If they were the same, it would have popped out when we checked the same. But if they're different, we definitely want an error. Okay, so check joint type. All right, and guess we're doing custom type. My type values let's say x and y, and and elm type dot custom type my other your type with values x and y should be an error. Keep doing that. Parenthesis, comma, elm type command dot error. Check joint type. Yes, please. My type xy, your type xy should be an error. This will fail. I think it'll return my type xy. Yeah, my type, well, yx in a set is the same. Okay. This, I think, is just error at this point. I thought this was going to be harder. Okay. So if anything's an error, it's an error. If two types are equal, then the union of them is the same. If one's a float and one's a number, it's a float. Or vice versa. Otherwise, it's error because you didn't match. So right now, basically, if you have matching types, you're okay. If you have different types, they're only okay if one's a float, one's a number. Okay, I guess that's pretty accurate. We don't handle integers yet, so we don't have to worry about that. Okay, so we'll run all tests. It said 2 errors. Is there another problem? Okay. Yeah. So in Elm types dot joint type knows what to do. Okay. Right. And I think we can close this for now. I think what we want to do, though, I'm beginning to think a lot of our things will have types on them. So maybe that's the way to go. So here's if expression. He has conditions. His result is a type, and it would sure be nice to just know that. All right, so let's see if we can push this around. I don't know. It's not your typical refactoring, is it? Okay, so let's run this. Somebody didn't like it. Yeah, I guess somebody should be failing. Yeah, tuple. Okay. We define that as tree, right? Type. Okay, so we can just pull him in. if expression, and then I don't need to know the left and right. All right, let's build. Still gotta. Yes, and I pulled this, so let's just take left.type joined with right.type. Well, no, let's. Let's compute the type. I don't know. It's not a. Let's see, result type, and then we'll put it in the thing. Okay, now we should have a complaint about result type. This is result type of type Elm type. Okay. Should pass. It's not doing everything we want. We got. Okay. If test tree expression elm type dot number. Right, good. And now we want to apply it and enforce it. Okay, so I guess we can check what we've got. So we've we made if expr no or hold on to its type. Okay, and now we want to enforce the semantics here. Test with two integers has type number. Test if with, well, two integers has type number. Let's get that part right. Elm type dot number. Yes. Right. Okay, so that's the fallout from our calculation of the joint type. We just took the joint type in, but we need to enforce rules about it too. So let's enforce that if with two types has an error, has type error. If true, then false, else two. Okay, and we should see a, oh, what do we get? Well, we should see an error in our whole tree, basically. The tree should be tree.error, I think. Okay, so it didn't do tree.error. It gave us if expression with true, false, and 2, then is not equal to error. So it just put this thing back. It didn't enforce the type rules, which is what we want to do. All right, so our next semantics is if result type is error, then we got a parser error. Okay. So if the condition type is wrong, if the joint type is wrong, I mean, I could make enforce semantics produce the result type. But I'm not going to. But notice here, result type is coming from this joint type calculation. That's doing all the work. So our syntax, our semantics enforcement is pretty simple. And we don't really use left and right. Can I make this a little better? All right, well, let's commit it. If statement checks that then and else clauses have compatible type. Let's make this thing take the tree that comes back. Let result equal this. Okay. And then return result. That's fine. I can do this down here. Result type equals that. Okay, enforce if semantics. That should be neutral. Forming that node is not a problem. Okay. But I think what I can do is pass the tree in now. Result. I'm just going to add the argument for a moment. Result of type tree. Okay, no one's referring to it, so no big deal. I don't know if that's any better, but I can say if, can I say result? I don't think I can do this, can I? Type tree has no member condition. Now that's sort of, where's tree? It's the if expression. Oh, it's a tree. I'm not sure this is coming out better, but let's assume it's an if expression, tree dot if expression. No, I don't think that's any better. Should still be green. No, I think that's good. All right. Oh, okay. Let's. Okay, I think we've done well. We've got our if statement, and it's parsing it, it's checking the syntax, and it's throwing exceptions if the semantics are wrong, which results in a tree.error. We would like better error reporting, and I think we'll deal with that probably next week. But we've got the semantics of the tree, I mean the pieces of the tree all captured and ready to go. I think what's next is we'd like to make it so it can interpret it. So this is a little funny. That really belongs on Elm type, I guess. But at any rate, if you got a tree and you had an if statement, right now we say unexpected input. All right, but we would like to handle if statements. So we'll come back and make our interpreter handle if statements. And I think that'll be a nice thing. We'll get to see a little recursion there too. But all right. So we'll just take 2 minutes and I'll see you in a minute or two. Welcome back. All right. So let's start with a test as we are wont to do. We got it. Test interpret if true. If when true. How's that? Check interpreter succeeds. Our input should be if true, then 3, else 2. And our expected output is 3 of type number. And we predict this fails. Okay, we expected that. We got nothing. And we got a message in there somewhere. Let's just run the one test. Unexpected input to interpret. All right. We have a case tree dot, and we're doing if expression with let condition, let left, let right, and the type. Okay. And this is pretty simple. I don't know, we got a little bit of I'm not sure how to deal with the well, let's see what happens, I guess. Okay. So what the semantics for an if is if you you should evaluate the condition, and depending on the condition, you return either left or right. Okay. And you got to evaluate one or the other. Okay. So let's let condition result equals condition, which is a tree. Well, what are we going to do with this tree? We're going to interpret it. Interpret the condition. Okay. And I'm not sure how to handle the booleans in here, but we're going to what are we going to do? I would really like to, well, in some case, if condition result, if something of condition result, has boolean, can we say that? Interpret gives us, oh, it does not give us a value at this point. Interesting. Okay. Maybe we want to start there. I don't know. I definitely would like interpret to give me a value. Is it going to give me a tree? I guess it kind of is. And who calls interpret? I guess our functions do. output is a string. Well, we don't want to see this every time we do this. I'm gonna extract. Let's see. I'm gonna copy. Okay, we're switching gears here. Let's block this test. Let me update my to-dos. Elm type.shared type. Compute their joint type. And we change the name. Require, then, and else clauses to be compatible expressions. Yes. And now we're at interpret the if, but I'm going to push something on the stack. Make interpret produce a primitive result. Okay. So I think our interpreter, let's take this out for a moment. Well, no, I'm going to comment this out for a moment. Okay. So what I would like to have is what we've said interpret does. I'm going to say this is evaluate. It's really more like print. Okay. I don't have an inline here, so I'm kind of annoyed. This part is print. So let me extract. And we'll call it print. Okay. Can I convert value? Okay, let's make this part of consistent. Output dot append can't handle ignored, and output dot append. Okay, and I think because those were just prints before, we should be the same. Okay, so we extracted a print method. I mean, it's REPL, read, evaluate, print loop. And really he's evaluate and print. Okay, so I guess I want an evaluate. Okay, let's say let result equal value dot evaluate, which doesn't exist, and we're going to print result. Okay, and we need a member evaluate, and I don't think it needs to be private function evaluate, and it's a input of type tree. And for now, we'll just return input. Is this compatible? Value type tree has no member. Evaluate. Oh. Yeah, we want to do this. Evaluate value. Oh. Constant result. Oh, I didn't return anything. Returns a tree. Okay. I think this is a better starting point. Let's take this thing and make it do some evaluation. We're going to switch on input. And tree ignored. Tree integer. I want to get all the things that are just going to return themselves. Integer and float and custom value. We're just going to return input. If we don't know what to do, we'll return input. Okay, I think can I do this? Case. Okay, so I'm splitting out the notion of what does it mean to evaluate a result and what does it mean to print a result, and that the normal process is you evaluate and then print. Okay, read is more like our compile. Okay, and to print a result, well, some of these things we just say it explicitly. We have explicit rules on how to do them. Okay, now we would not expect to print an if expression, and there's a lot of things we wouldn't expect to print. We expect to evaluate them. But yeah, so let's pull this out of print, and I think that's probably more accurate. Let's see if anybody was relying on that. I doubt it because it was originally a print statement. So okay, yeah. So now I think we're positioned to evaluate this thing. Let's take our test back. Take the X off. Should fail. Three is not equal to unexpected input to print. Okay, because it didn't get evaluated. All right. So now we can get this case. If you get an expression we want to take, let the condition result equals, we want to do evaluate of condition. Okay. And if condition result equals, and then I don't know what we're going to say here. It's got to be, well, it's got to be a custom value. Yeah. Custom, where's our tree? Custom value. Okay. I don't know if we can ask our tree is as boolean. Let's assume we can. Okay, so if we get a custom result, as boolean. We're going to do one thing, else we're going to do another. Okay. This type on the tree, maybe we don't need it. All right. Okay, so if you evaluate the condition and somehow you judge it as a boolean, and if it's true, then you want to return evaluate of the left, and if it's false, you're going to return evaluate of the right. Okay. And yeah. So eventually, these things return values that are primitive values, and this is really the primitive stuff. Okay. Evaluate left. Oh, interesting. We have to worry about the type of this result. I'm not sure how we're going to do that, but let's get through this part. It's feeling like just on the edge of control here as to what's going on. So, this is the right semantics for an if, I believe. So we need to say condition result, which is of type. Should be a tree, right? Yeah, it's a tree. Okay, so if tree has a as boolean method, we need to get that. Okay, so if extension tree as boolean returns bool. Okay, and if let if case let I know we've got case let elsewhere here. Where's my global find? Case let. Ooh, that's the only one. Okay. Let's look it up online here. If case let Swift. If case let name with lets on it. Okay. If case let is an abbreviated switch. I guess if case and then put the lets inside. If case, we care about custom value. Let value, let type. Equals self. Then do something. Okay. We're going to say false otherwise just to default something. But okay, if we get the value, I don't think we need to use, we don't need the type. Well, no, we do. Okay. It's like, where are we going to find out about Boolean? This is tough. Okay. This thing's a custom value. If type is elm type dot custom type with Boolean, like what the heck, right? False, true. Well, if that's true, and we're going to return a value, okay, so if this thing is a custom value, then it's got a value and a type. The type has to be custom type bool false true. If it is, and the value is true, then it's true. Otherwise, we're going to just say it's false. All right, here we go. Oh, it doesn't even compile. Input 3 number. Whoops. Let's see this. Type was never used. Well, that's another issue. Okay, so we're evaluating if statements, I think. Yes, okay. So evaluate if statement in interpreter. Okay. Yeah, so we evaluate left or right. Now, the thing is, this result type can get messed up. So let's try and get a situation here. So if I do float and an int, what's the type? We did that before. 3.5 else 2. Okay. Notice this to a float. 2 by itself is just a number. Okay. And so it computed their joint type to be float. And so it should be returning to float, not to number. Ours returns to number. Let's see that happen. Okay. It's kind of a subtle thing. Interpret if well, it yields joint type. Okay, let's do this way so we can see it failing. Put this in the REPL. Okay, we should get 3 float, even though normally by itself 3 is just 3 number. Okay. So we have to basically we kind of like cast it, I guess. That's probably the most accurate way, and this will fail. With 3 number. Yeah. Okay, so interpreter, it's going to need to cast it. It's going to need to cast its value to the new type is basically the result. So I'm going to say cast to type. And we'll do both branches. Well, we'll do them. We'll do a separate test. Okay. Let's see. So cast is something that takes a tree and a type and forces its type to the new type. Ugh, it's a little weird. And I really wish Elm had just kept its ints and floats separate, but they target JavaScript, so they merge those two types kind of easily. Okay, so we need a function cast. Let's do that. Function cast it applies on a tree and it gets a type of Elm type. Okay, so given a tree, like tree float or tree int or whatever, well, this should only happen. When can it happen? It only has an effect with numeric types. All right, so let's switch on self dot. Let's switch on self. Okay, and we got all these cases like tree dot integer. And well, that's the one we're working on now, right? And it's got a default. Okay. The default result is you just return self. You don't need to cast. Okay. But if you happen to have an integer, we need to return a new integer. We do have a failing test. Okay, so return a new integer with the new type. All right. So this is basically somebody's saying you got an integer, you convert it to number, got an integer converted to float, things like that going on. Somebody's making that decision. In this case, it's the if case. We know the joint type, and the result has to be of the joint type. So it always, I don't know, is that broadened or narrowed? But it always takes that joint type. Okay. And value of tree has no member cast. Well, it does now. Oh no, this is the wrong place, isn't it? Okay, so this should be on tree. Okay, so casting a tree to an elm type says, look at yourself. Are you a tree? Are you an integer tree? If you are, we're going to make a new integer tree with your value, but the new type. Or we're just going to return self. All right. And this should pass now, I hope. Okay. And let's flip it. Well, we'll just take the other case. All right, let's take if false, then can we get somebody forced to a float? The joint type of number and float is float. Okay, this should fail because we only did the one side. Okay. Left, and then cast the result to a type. Okay. And should pass. Oh, it did not. We got, oh, yeah, well, you do have to put the right value in. False should get the second arm or the third arm and get the new type. All right. So we make if force cast its result to the joint type. All right. This is a good moment for things. Let's rearrange some stuff. So interpret, I want to basically tell the story from the top to the bottom. That's a little helper thing. All right. Interpret calls evaluate and then calls print. Whenever you've given it a tree, print knows how to handle primitive types, kind of leaf types, but it doesn't handle stuff that needs to be evaluated still. So it's the result of a computation. It's probably going to be an int or a string or a float or a list. It's not a computation in progress. Whereas this is, okay, so that's all right. Basically, constants get their own value, and if statements do the computation we expect. Can we make this better? Well, I could say let result of type tree result equals this. Result equals that. Spell it. And then return result cast of type. Is that better? Yeah, let's clean up in interpreter.swift. I guess these are refactorings. Okay, now this one, format a type. Whew, boy, it is Elm type should be aware of that itself, maybe. Who calls format type? It must be this thing, right? Well, it's always calling format type of type. Let's pull this into Elm type. See, the argument is all it worries about is the value. So I think I can say that's reasonable. Elm type. It won't be private. Now, I don't know. This may not be the right way to get a string out of it. All right, but we have a format type there, and now this thing, I think it should call type dot format type. Type.format type missing argument. Oh. We'll clean that up in a moment. Good. Okay. All right. So we moved format type from interpreter to Elm type. That's a move method refactoring. Okay, how's interpreter? All right, the output thing's a little goofy. Nobody should be calling this anymore. Okay. All right. I think that's decent. We still have some goofiness. This has Boolean thing. I don't know. We're gonna have to. Um, we're gonna have to fix that. Maybe we can get this in a one-liner. Is that gonna be better? Result equals this. Then evaluate left. Else evaluate of right. I think that's an improvement. Okay, refactor. Switch from if to ternary. I don't know. It's the only ternary operator you get. There must be others. Okay. I'm gonna call it a wrap then. I think there's still stuff to work out. This Boolean, how we're getting those values. I mean, yeah, we've got some stuff to work out. The interpreter really, it needs more than just the tree. It also needs like the symbol table, the set of names that have been accumulated and stuff like that. I would like to reveal that. I think we can get there next time. Um, well, I think we may stop and improve our error handling because already it's like it blew up somewhere. So anyway, next time is Tuesday, 1 to 3 p.m. Eastern time. Thank you for joining me today, and I hope I can see you in the future. Take care. Bye bye.